What if you could monitor thousands of industrial assets spread across multiple locations without ever stepping inside the plant? From manufacturing facilities and power plants to oil and gas operations and critical infrastructure, organizations are increasingly relying on remote monitoring to gain real time visibility into their operations, reduce downtime, and improve productivity. In this video, we will break down how OT remote monitoring works, the technology behind it, the most popular tools used across the industry, and the real world benefits organizations are experiencing. Whether you are an OT engineer, IT professionals, cybersecurity specialist, or simply curious about Industry 4.0, this session will give you a practical understanding of one of the most important technologies driving modern industrial operations. So let's get started. Remote monitoring in the operational technology industry refers to the ability to observe, analyze, and respond to the status of industrial assets and process from a centralized or remote location. OT environment include factories, power plants, oil and gas facilities, water treatment plants, and transportation system where physical processes are controlled by equipment such as PLCs, RTUs, sensors, actuators, and SCADA system. Traditionally, these environments relied heavily on on-site operators and manual inspections. However, with increasing scale, geographic distribution, and complexity, organizations have adopted remote monitoring to gain continuous visibility without being physically present at every site. At its core, remote monitoring bridges the physical and digital world. It captures real time and historical data from machines and process, transmits the data securely over industrial network, and presents it through dashboards, alarms, and analytics tools. This enables operations teams, maintenance engineers, and management to understand what is happening across multiple sites at any given time. Remote monitoring is not only about viewing data, it is about early detection of anomalies, faster incident response, and informed decision making based on accurate operational insights. The importance of remote monitoring has grown significantly with the convergence of IT and OT, the rise of Industrial Internet of Things (IIoT), and the need for higher uptime and safety. Industries now operate in highly competitive and regulated environments where unplanned downtime, safety incidents, or environmental non-compliance can have severe financial and reputational impacts. Remote monitoring supports proactive maintenance, improves operational efficiency, and enhances safety by providing timely alerts and situational awareness. As a result, it has become a foundational capability in modern industrial operations and a key enabler of Industry 4.0 initiative. Illustrative dashboard style image representing centralized visibility of OT assets, trends and alarms across industrial operations. If we talk about what is OT remote monitoring, then it is the continuous observation of industrial assets, process and environments using digital technologies that collect and transmit operational data to a centralized platform. Unlike IT monitoring, which focuses on servers, applications, and networks, OT monitoring deals with physical process such as temperature, pressure, flow, vibration, energy consumptions, and machine states. These parameters are directly tied to the health, performance, and safety of industrial operations. In practice, OT remote monitoring involves connecting field devices such as sensors, PLCs, RTUs, and intelligent electronic devices, to supervisory systems like SCADA, Historian, or IIoT platforms. The collected data is then visualized through human machine interface or HMIs, web dashboards, or mobile applications. Operators can view real time values, analyze historical trends, and receive alerts when predefined thresholds are exceeded. This allows teams to understand not only what is happening now, but also how systems are behaved over time. A key distinction of OT remote monitoring is its emphasis on reliability, determinism, and safety. Industrial systems often run 24 by 7 and control critical infrastructures, so monitoring solution must be non-intrusive and highly reliable. The goal is to gain visibility without disrupting control logic or introducing risk. OT remote monitoring supports multiple stakeholders. Operators gain situational awareness, maintenance team detect early sign of failures, engineers optimize processes, and management gains high-level performance insights. Together, these capabilities transform raw operational data into actionable intelligence that support smarter, safer, and more efficient industrial operations. Remote monitoring in OT environment follows a layered and structured flow, starting at the physical process and ending with actionable insights for users. The first layer is data acquisition, where sensors and instruments measure physical parameters such as temperature, pressure, vibration, flow, voltage, or motor speed. These sensors are connected to controller like PLC, RTU, or DCS controllers, which execute control logic and collect raw operational data. The next layer is communication and data transport. Industrial protocols such as Modbus, Profibus, Profinet, DNP3, OPC UA, and MQTT are used to move data from controller to higher level systems. In modern architecture, industrial gateways or edge devices aggregate data and securely transmit it over plant networks, wide area network, or the internet. This data may be sent to on-premise SCADA systems, data historians, or cloud-based IIoT platforms, depending on the architecture and business requirement. Once data reaches the monitoring platform, it is processed, stored, and visualized. Dashboards display real-time status, trends, and key performance indicators (KPIs), while alarm engines evaluate data against thresholds and generate notification via HMI pop-up, emails, SMS, or mobile apps. Advanced systems apply analytics, machine learning, or rule-based logic to detect anomalies and predict failure. The final step is human action. Operators investigate alarms, maintenance teams plan interventions, and managers make data-driven decisions. This end-to-end flow enables continuous visibility and timely response across distributed OT environments. Simplified OT remote monitoring architecture showing data flow from field devices and controllers through gateway to centralized SCADA or cloud platform. Remote monitoring delivers significant business and operational benefit across industrial sectors. One of the most important advantages is reduced downtime. By continuously tracking equipment health and process parameters, organizations can detect abnormal conditions early and address issues before they escalate into failures. This proactive approach minimizes unplanned outages and production losses. Another major benefit of predictive and condition based maintenance, instead of relying solely on fixed maintenance schedules, team can use real time and historical data to assess the actual conditions of assets. Parameters such as vibration, temperature, and energy consumptions provide early indicator of wear or malfunctions. This allows maintenance activities to be planned more efficiently, reducing maintenance cost and extending asset life. Remote monitoring also improve operational efficiency and resource utilization. Centralized visibility across multiple sites enables benchmarking, performance comparison, and optimization of process. Fewer site visits are required, which lowers travel cost and improve workforce productivity. From a safety and compliance perspective, remote monitoring enhances situational awareness in hazardous or remote locations and supports regulatory reporting through accurate data logging. Collectively, these benefits translate into higher reliability, lower operating cost, improved safety, and better decision making for industrial organizations. A typical OT remote monitoring architecture is composed of several well defined layers, each serving a specific purpose. The field layer includes or sensors, actuators, motors, valves, and other physical devices that interact directly with the industrial process. These devices generate raw data and execute physical actions based on control commands. Above the field layer is the control layer, which consists of PLC, RTUs, and DCS controllers, along with safety systems. This layer is responsible for real time control, interlocks, and automation logic. It is designed for high reliability and deterministic behavior. The supervisory layer sits on the top of the control layer and it includes SCADA systems and HMIs. This is where operators monitor process status, acknowledge alarms, and perform supervisory control actions. In modern architecture, data from the supervisory layer is forwarded to data historians and IIoT platforms, either on premise or in the cloud. Historians store large volumes of time series data for analysis and reporting, while cloud platforms enable advanced analytics, cross-site visibility, and integration with enterprise systems. Network segmentation, firewalls, and secure gateways are used to separate and protect these layers. This layered architecture ensures that remote monitoring enhances visibility and insights while preserving the safety and stability of core control functions. A wide range of tools and platforms are used for OT remote monitoring depending on industry requirements, scale, and architecture. SCADA platform remains central to many deployments. Popular SCADA solutions include Ignition, Aviva Wonderware, Siemens WinCC, and GE iFix, which provide real-time visualization, alarm management, and control integration. For network and infrastructure level monitoring, tools such as Paceler PRTG, Zabbix, SolarWinds, and DataDog are increasingly used to monitor OT network, servers, gateways, and communication health. These tools help identify network issues, latency, or device failure that can impact operations. In parallel, cloud and IIoT platforms like Azure IoT, AWS IoT Sitewise, and specialized IIoT solutions enable large-scale data ingestions, analytics, and remote access across geographically distributed assets. OT security and anomaly detection tools have also become critical component of remote monitoring. Platforms such as Clarity, Nozomi Network, and Dragos focus on asset discovery, traffic analysis, and threat detection in OT environment. Together, these tools form an ecosystem that supports visibility, performance monitoring, analytics, and security, allowing organizations to build comprehensive and resilient remote monitoring solutions. Visual representation of commonly used OT monitoring, SCADA, cloud, and security tools across industrial environments. Remote monitoring is applied across a wide range of industrial use cases. In manufacturing, it is used to monitor production lines, machine utilization, quality metrics, and energy. Energy consumptions. Real-time visibility helps optimize throughput, reduce scrap, and quickly respond to equipment issues. In utilities such as power, water, and wastewater, remote monitoring supports geographically distributed assets like substations, pumping stations, and treatment facilities, ensuring reliability and regulatory compliance. In the oil and gas sector, remote monitoring is essential for pipelines, wellheads, compressor stations, and offshore platforms. These assets are often located in remote or hazardous environments, making continuous on-site monitoring impractical. Remote systems provide early leak detection, performance monitoring, and safety alerts. Renewable energy operations include wind farms and solar plant, which rely heavily on remote monitoring to track generation performance and equipment health across large areas. Cybersecurity is a critical consideration in OT remote monitoring, especially as industrial system becomes more connected. OT environments were historically isolated, but remote access and IIoT connectivity have expanded the attack surface. A successful cyber incident in OT can have physical consequences, including production shutdown, equipment damage, or safety hazard. Key security principles include network segmentation and defense in depth. OT network should be segmented from IT and external network using firewalls, demilitarized zones (DMZ), and secure gateways. Remote access should be tightly controlled through VPN, multi-factor authentication, and role-based access control. Continuous asset inventory and monitoring help organizations understand what devices are connected and detect unauthorized changes. Specialized OT security monitoring tools analyze network traffic and device behavior to identify anomalies and potential threats without disrupting operations. Regular risk assessment, incident response planning, and alignment with standards such as IEC 62443 further strengthen security postures. By integrating cybersecurity with remote monitoring strategies, organizations can achieve visibility and efficiency while maintaining safety and resilience. The future of OT remote monitoring is closely tied to the evolution of Industry 4.0 and digital transformation. One major trend is the increased use of advanced analytics and artificial intelligence. Machine learning models are being applied to operational data to enable more accurate predictive maintenance, anomaly detection, and process optimization. Edge computing is another important development. By processing data closer to the source, edge devices reduce latency, minimize bandwidth usage, and allow faster local decision making while still supporting centralized monitoring. Digital twins, virtual representation of physical assets or processes, are also gaining traction, enabling simulation, what if analysis, and deeper understanding of system behavior. Finally, greater integration between OT and enterprises systems is expected, providing end-to-end visibility from the shop floor to business operations. As standard matures and security practice improve, remote monitoring will become even more scalable, intelligent, and integral to industrial operations, supporting higher level of automation, efficiency, and resilience. Remote monitoring has become a cornerstone of modern OT operations. It enables continuous visibility into industrial assets and processes, supports proactive maintenance, improve operational efficiency, and enhances safety across a wide range of industries. By leveraging sensors, controllers, industrial network, and monitoring platforms, organization can transform raw operational data into actionable insights. Successful OT remote monitoring requires a balanced approach that consider architecture, tool selection, cybersecurity, and organizational process. SCADA systems, IIoT platforms, monitoring tools, and security solutions. They must work together within a well-designed segmented architecture. At the same time, people and process must be aligned to act effectively on the insights generated. As industries continue to evolve toward more connected and data-driven operations, remote monitoring will play an even more critical role. Organizations that invest in robust, secure, and scalable remote monitoring solutions will be better positioned to achieve reliability, efficiency, and competitive advantage in an increasingly complex industrial landscape. So hope you got to know a detailed overview of how remote monitoring works in operational technology world. For more such videos on deep energy or engineering tech, subscribe to Conversed World and we will see you in the next video. Thank you.